Today we're going to talk about the difference between rotational quantities and translational quantities. Up to this point we've been dealing with translational motion. Translational motion means you're moving from one place to another place, displacing yourself, or the object will displace, right? Go from one location to a separate location. There's no change in its orientation. If you're going to draw a velocity arrow, that velocity arrow would point in the same direction during that entire motion. And it's generally, we consider it to be linear. Even when we're talking about circular motion, we're displacing around the edge of a circle. Okay? So a lot of times that's considered to be translational also. But now we're going to focus on rotational motion, which is movement around a fixed point. It's when something is turning on an axis, which is different from circular motion. So if I move this in a circle, the pen would follow a circular path. If I rotate it, though, then I'm doing this. You see the difference between those two? So translational motion is actually going over, traveling a distance. Rotational is turning about an axis or spinning. So some rotational quantities are angular displacement, angular velocity, angular acceleration, rotational inertia, rotational kinetic energy, angular momentum. You see, they have the same vocabulary words generally as we've been using for linear motion, except now we either put the word angular or rotational in front of it. They do have different symbols. Theta for displacement, omega for velocity, alpha for acceleration, etc. These things we'll do another time. But here's what they mean. So if I start at point A and I move to point B, I have displaced through this angle. Now this angle, we generally have been using degrees, but when you're talking about rotation, the units is radians. So we've displaced a certain number of radians. Now if it's 90 degrees, how many radians is that? That's pi over 2 radians. If you displace all the way from A around back to your starting point, then you've displaced 2 pi radians. So it's in a different terms, but it's the same meaning as degrees, really. So that's what displacement is. You're carving out the angle around that central point. Velocity is how fast you carve that point out, or as you carve that angle out. So you're going to cover a certain amount of displacement in a certain amount of time. The faster the time, the faster your speed. The less the time, the faster the speed, and so on with these other quantities. Converting from rotational to linear quantities, you can see, is fairly systematic. You take the units, the quantity you have, which would be angular displacement, you multiply by the radius, and that will give you your linear distance. So if you want to convert from the angle that's carved out to how far you've gone around that outside of that circle, which would be some portion of the circumference, you multiply by the radius. And same thing with angular speeds. You're going to multiply by the radius to give you your linear speed, and same thing with acceleration. Most things follow that general trend, but there are some exceptions which we'll get to shortly. I want you to look at these rotational kinematics equations, and I will hope that you notice how similar they are in structure to the linear kinematics equations we have. They are identical except with the angular terms in them. So omega equals delta theta over delta t. Well, that's the same or analogous to our constant speed equation that we use for linear motion. Alpha equals delta omega over delta t. Well, that's analogous to acceleration equals change in velocity over change in time. And you can do that for all of the kinematics equations. And they're used exactly the same way. You're just dealing with different units, radians, radians per second squared. But it's not any harder than that. But the main thrust of this lesson is about torque. Torque is the force that causes rotation. So This is the only one that isn't called like angular force or rotational force. This is called torque. It has a special name. And it's the force that causes rotation to occur. So you're going to apply a force, and it needs to be some distance from your pivot point, which is called a fulcrum. So this length here, the length, I have a board here, but it could be anything, right? This length is called the lever arm. Whether it's a lever or not, it's still called the lever arm. This lever arm, right, is the distance is R between the pivot and the force. So where you put this fulcrum matters, because if I move the fulcrum to the middle of this board, it makes my lever arm shorter. If I move it to this end of the board, right, then I'm pushing right on the fulcrum. I'm not going to be able to get much, I'm not going to be able to get any torque. It won't rotate at all if you do that. Now, when we're talking about direction of torque, we're talking about clockwise or counterclockwise. Around the clock this way relative to the fulcrum, or around it that way. Counterclockwise is considered positive, and clockwise is considered negative. So this is the equation. Torque equals force times radius times sine of theta. Torque is a tau. It's a Greek letter, T. Okay, this is the applied force, the force that's applied to cause the rotation. This R is the distance between the fulcrum and the force you're applying along that lever arm. And this theta is the angle between this force and the lever arm. So in this case, it's 90 degrees. If you applied the force this way or that way, it would be a different angle. So how can we maximize torque? Torque can be maximized by making this bigger, right, the force, using a bigger application of force, by increasing the distance between the force and the pivot point, or making the angle 90 degrees, because that maximizes sine of the angle. So think about opening a door. So when you open a door, you walk up to the handle and you always push at right angles to the door to open or close it. You don't try to do it from the side at an angle. It's a lot harder to do. You always try to do it head on because it's easier, and you know that it's easier. The handles are almost always at the very far edge of the door. Handles that are in the middle of a door don't give you nearly as much leverage, we call it, or you don't get as much torque for the force that you apply. So here's a typical example or set of examples. So how much torque is needed to turn a nut using a wrench? You can push with a force of 100 newtons, so we'll keep it simple. So here's your force being applied, right? You do it at the very end of the handle, and your pivot is right here, right where the nut would be, because that's the thing that you're rotating around, this center point, right there, each time. And so if you have a short wrench that's only 10 centimeters, you have to you only get a torque of 10 newtons per newton meters, right? Force times distance is newtons times meters. There's no special units for this. If you have a longer wrench, you get more torque, 20 newtons times meters. And that means that you're going to have an easier time because you get more torque given a set force. And the more torque, the easier it's going to be to rotate. Here, if you try to apply that at an angle, like let's say you're trying to do something and it's like inside and you can't really reach well, and so you have to kind of like reach in and apply your force but not straight down, you're doing it off at an angle, well that's going to reduce your force because now instead of sine of 90, you might have sine of 45 or sine of 60 or so. Any angle smaller than 90 will give you a sine of the angle that's less than 1, and so it's going to reduce your net torque on that. So you get 10.6.